Hey, in this video we're going to talk about unbounded loops, why they're so dangerous and how they can literally lock funds away in a smart contract, in a protocol, and unless we upgrade that protocol or that contract in some way that we can actually retrieve the funds after upgrading that smart contract, those funds are going to be locked in that smart contract forever. So yeah, let's explore how unbounded loops work. Let's explore a code example that I have prepared here in Remix. As always, we have a vulnerable distribution contract, which I'll go over after I've explained the basics of unbounded loops and why they happen, why you should avoid them. And then we have also got an attacker contract as well that we're going to deploy. We're going to see the interactions between the two of them, and then I'm going to show you a contract that is not as vulnerable as this vulnerable distribution contract right here. So without further ado, let's actually start by talking about unbounded loops. I want you to understand that an unbounded loop is basically a loop that can grow infinitely. So it doesn't have boundaries. It doesn't say, okay, I'm going to run maximum 10 times or maximum 100 times. It just grows and grows and grows, and the loops basically just performs itself over and over and over, and it can reach literally unlimited loopings or unlimited iteration of that exact same loop. So in a vulnerable contract where we have unbounded loops, we would have a setup that is similar to the following. So we will have a function, obviously, but then we will have an unbounded array. An unbounded array is just an array that doesn't have a maximum. Okay, so you could add as many addresses in that array, as many strings, as many integers, whatever you want, as many booleans in there. You could add as many items in the array as you wanted. Okay, so there is no limit as to how many items you can get in that array. And then obviously, if we are iterating over that array in a loop, that immediately becomes an unbounded loop. Why? Because literally there is no limit to how many pieces of information, how many pieces of data we can have in that array. So the loop, if we iterate over that array, is just going to grow infinitely. Okay, so the function that uses the loop and the array inside of it is a little bit tricky. It's a little bit dangerous, okay, because it can get exploited. And in fact, with an attacker contract that exploits the loop, that function can be exploited. And obviously gas cost increase per transaction in Solidity. So the more you run that loop and the more stuff you do inside of that loop, the more expensive it's going to be to perform that iteration of each loop. And it's just going to become a mess. It's going to become a mess because, one, if you don't hit the gas limits, it's going to be pretty damn close and it's going to be pretty damn expensive. Okay, it's going to be pretty damn expensive to run that function, and it's not a very good user experience for users to have to pay a lot of gas. Okay, it is not good. And if on the other side it hits the gas limit, it's not going to be expensive because it's going to revert because it has hit the gas limit. But then when the block gas limit gets hit, the function becomes uncallable. Why? Because Ethereum doesn't allow you to call a transaction, to perform a transaction that exceeds the gas limit. So that limit is there for a reason, and is to prevent like other types of spam and stuff like that. I'm not going to get into it right now, but you should definitely look into it a little bit. But the gas limit is there for a very specific reason. And obviously, if you are going to perform a transaction that is going to run over, that is going to go over the block gas limit, Ethereum is not going to like it and is going to, or the EVM is not going to like it and is going to essentially revert your transaction. Okay, so without further ado, let's go into the code. Okay, let's actually dive into the code. I'm going to see if I can zoom in a little bit. Yes, there you go. There you go, so you can see it better. So we have this vulnerable distribution contract right here. Let me actually move this Loom stuff right out of the way. Awesome. So we have this vulnerable distribution contract. It has got an unbounded array, like I said earlier. It has got an array of addresses that can grow unlimitedly without boundaries. Then we have got a mapping that matches the user with a true or false value, which is basically if the user has registered in the protocol or not. Then we have got a register function. Now, I'm going to say this, but to make the example easier for you guys to see and for me to be able to run it, I have not done any type of checks like In this case, a user, the same user with the same address, can register multiple times. Obviously, in a production ready code base, you wouldn't want to do this. But yeah, I just wanted to let you guys know, okay? Then we have got a deposit function, which allows a user to deposit Ether into the contract. Then we have got a distribute rewards, which is external payable, and it essentially calculates a share based on the balance of the contract and based on the users or the length of the users array. And then for each of the users in the users, for each of the users in the users array, we are going to, it's so complicated to do this stuff. We're going to do a transfer of Ether, okay, with the call method. And obviously this is quite expensive, not only because we're having to essentially read the array in memory, but we're also having to perform a transfer here with the call method, which also is quite expensive to do, especially doing it in a loop. Okay, if you do it in a normal function, like in a regular just one transfer, and you do just one call, that is fine. That is expected. Like, you know, however much that costs, it costs. But yeah, in a loop it can get pretty expensive. And then just to get our function to get the user count, just so we can see how many users are in the users array. And then we've got an attacker contract, and we're obviously going to pull the vulnerable distribution as a target. We're going to pass it in the constructor. Then we're going to create an attack function with a number of iterations that we're going to decide. And obviously this cannot hit the block gas limit either. And yeah, we're just going to run a loop, and then we're going to register as many addresses as iterations we have in this function, or as we pass in the function. And then we have a receive function in here, just so we can receive the Ether from this call method into this contract. Okay, so with account number one, we're actually going to deploy vulnerable distribution. That sounds about right, with 3 million, and I'm going to do 3 million gas limit. Normally in the EVM in Ethereum is 30 million, but just for testing purposes, we're going to do 3 million. Okay, so let's deploy this. It was successful, and now we're just going to call register, just to make sure that we can register someone in there. Cool, awesome. Let's get the user count. That should be 1. Perfect, awesome. So now we're going to copy this address, and with a different account, we're going to deploy the attacker contract. Let's paste the target address in there. Let's deploy this, and now we're going to call attack. Okay, and we're going to pass maybe, let's say 500. Yeah, let me do 1,000. Let me see if that doesn't hit the block gas limit. Let's transact, see if that works. If not, we'll have to do it with it now. Yeah, not enough gas. Okay, so let's do 500. That should go through. Let's see if it does or if it doesn't. Yep, and let's call it a bunch of times, okay? 2. There you go. It's gone through. Let's do another one. Let's do another one. Let's do another one. I'm going to do a couple more. I might have to cut this or edit this or whatever. But yeah, it is quite the work in here. Let's do another one just for fun. All right. So now once that transaction has gone through, which we're going to wait just a second for it to go through. Let me see. There you go. There it goes. Awesome. So now if we switch back to account 1, let's call again, where is it here, vulnerable distribution. Let's call again get users count, and there's 3,000 users in there. Okay, so our user base has grown quite significantly. But now what we're going to do is call this distribute rewards contract, okay, which function, which is going to calculate a share based on the address of the balance of the address. Which, by the way, let's actually fund this contract, because right now we have got 0 Ether in there. So let's deposit some Ether. Let's do, with this account number 1, let's do 10 Ether. Okay, let me see that goes through. Perfect, that has gone through. And now we have funded the contract, okay, with 10 Ether, and we have around 3,000 users inside of this protocol, inside of this vulnerable distribution contract, and we're going to call distribute rewards. Now what this will do is grab 10 Ether, divided by the length of the user's array and calculate a share based on this division. Okay, and then what it's going to do is try to transfer the share to each of the users inside of the array. But if we've done it correctly, we will see that it indeed fails because it's going to run out of gas. Okay, it's not going to have enough gas to distribute the rewards to all the users. Let me make this terminal a little bit larger in here. Let me clear the terminal and let's go distribute rewards. Let's transact and see what happens. It's gonna take a minute, and there you go, it failed because it ran out of gas. There you go, transaction ran out of gas, please increase the gas limit. So as we can see here, if we go to the drop down, transaction cost, 3 million gas. So it literally touched the upper boundary of the gas limit. It hit the gas limit, so the transaction is never going to go through. Okay, it's never going to go through. And as we can see now, this distribute rewards function is uncallable. So 10 ether would permanently be locked inside of this vulnerable distribution contract, which is not what we want. Okay, it is not what we want, and we have got no way right now of like getting rid of addresses in this address array. We have got no way of nothing. We cannot call this function anymore. Okay, we cannot call this function anymore because the attacker has made the user's array so big, so large, that every time that we try to call the distribute rewards function, it's just going to run out of gas. Okay, so what do I recommend you do in this cases? Because obviously we would want to allow users to retrieve their share. Okay, but there is a much better way of doing it. It's called the push over pull method. Okay, so what we're going to do is we're going to allow the users to claim their rewards individually, and we're not going to do a massive loop with all the users, and we're not going to let the smart contract just take care of that logic of sending the ether in just one single loop. We're just going to let every user claim their reward back. So it's up to the users if they claim or if they don't claim. If they claim, they're going to get their ether back, the deposit back, or whatever share they are allocated back. But if they don't claim that share, if they don't claim that reward back, their ether is just going to stay in the contract until they do indeed claim it back. Okay, and instead of using an array, we're just going to use mappings. Okay, we're going to use mappings, and we're going to map a user to a Boolean value to see if it's registered or not, and a mapping that is going to keep track of its user and see if the user has claimed the reward or not, and then a U256, which is going to be the number of active users. Okay, and as we can see, we have got the sort of like the same functions, but I've enhanced them a little bit. The register function now has a check, and we're going to change the status of the message.sender, and it's going to be registered, is going to be equal to true, and then we're going to increase the number of active users. The deposit function is still the same. Now the claim reward has got two checks in here. Now we calculate the share based on the address of the balance of the current contract, so the distribution contract, and then we're going to divide it by the active users, and this is going to give us a share. We're going to change the state of the claimed mapping to be equal to true. We're going to decrease the number of active users because that is going to affect how we calculate the share, and then we're going to perform the transfer. So as we can see, it's much leaner. It is not ever going to use as much gas as this will, and when possible, it's much better to use mappings over loops or over unbounded arrays. Okay, because with unbounded arrays, you're just going to end up in a situation where you are probably going to have to use a loop, and if you're not careful, that is going to not be a good solution for you, because at the end of the day, if you're not careful, you can run into this issue of unbounded loops, and if a function just runs out of gas every time, it's just not going to be callable, and funds can be permanently locked in a contract forever. So yeah, that was it, guys. That was it for unbounded loops. I hope you enjoyed it. I am creating a GitHub repo. I just got a lot of stuff going on right now, but I am creating slowly but surely a GitHub repo with a bunch of smart contract vulnerabilities that hopefully I'll be able to share with you guys soon. And as soon as it's ready, I'll just post it in the comments or in the description of the video down below. And yeah, of course, I'll let you know when I got it done. So I hope you enjoyed the video, guys. And if you did, just make sure you smash that like, subscribe to the channel. I'll keep posting videos like this because I think this is super interesting stuff. And anyways, I will see you guys on the next one.